Okay, good afternoon. Welcome everybody to the weekly M-Cubed seminar. Today we're very fortunate to have Zeljka Stone from the New Mexico Institute for Mining and Technology. Zeljka received her PhD from New Mexico Tech in 2005. 2007 to 2011, she was had appointments at the Faculty of Science in Split, Croatia, where she was vice president for a couple of years. Since 2018, she's been a research associate professor and director of the Climate and Water Center at New Mexico Tech. Zeljka's work is concerned with the understanding of the interplay of convection and tropical disturbances, including equatorial waves, the MJO, and tropical cyclones. A most recent project she's been involved in is the project coordinator and manager for the field project organization of Tropical East Pacific Convection, OTREC, in 2019, studying the diversity of convective behavior, the vertical structure, spatial distribution of convection in the Eastern Pacific Ocean and the Southwest Caribbean, regions that are less understood than the other regions of the tropics. Today, I'm looking forward to our seminar on convectively coupled equatorial waves. Zeljka?
Thank you, Rich. So the last time I was here, I think, was just before COVID, March. Right after that field project, OTREC, I came here to give a talk on OTREC. And we were talking about COVID and wondering whether there will be another field campaign happening. And I was all like, I'll go, just send me. And then the whole country shut down. On a more positive note, let's today talk about something completely different than field projects. And that's going to be convectively coupled equatorial waves. And I don't know how much background you have, but I have heard that this month has been a month about tropical disturbances. So I'm hoping you do have some background into what I'm going to talk about today. But primarily, I have divided my talk in kind of three parts. One is going to be what happened back in 1966 when we imagined our atmosphere as without convection. Then I'm going to talk about the last 20 years of my research when it comes to convectively coupled waves. And then I'm going to try and convince you that there are two models out there that can model convectively coupled equatorial waves that have different physics or different starting points, but in essence, they say the same thing. So let's start with 1966. And some of you know this, and I'm going to try to point with this. But I'm just really going to ease into it. So Matsuno in 1966 developed this model. It was linearized shallow water equations on an equatorial beta plane with an adiabatic atmosphere. Other words, no convection, so just adiabatic atmosphere. What he did was he defined x and y, and he defined some average height. The perturbation around that height is this little h, and u and v are zonal and meridional velocity. And so if you linearize that on the shallow water, you get this system of equations. So the momentum equations and this equation for the perturbation over the height. Simple enough, right? So this simple, really simple set of equations, when you impose this kind of dependence on x and time and solve for y, solve for v as a function of y, you are going to get this solution. But let's stop for a second here. So every time you have PDEs, right, you either have to uncouple them somehow or you have to make certain approximations. This is a very standard approximation for x and time. Most people use minus here. Matsuno liked plus. So that's going to change when I show the results. I'm going to point out this is westward or eastward propagating, depending on what we took here. But this is really a simple math, like PDE problem that any student could solve. This is the differential equation you get. Omega is the frequency that comes from here, and k is the wave number that comes from here. So this equation has this kind of a solution where h sub n is the Hermite polynomial, and this n is very important when we look at the convectively coupled disturbances, or not convectively coupled yet, because it can tell us whether it's symmetric or anti-symmetric around the equator. All right, so obviously, I don't know if it's obvious, but it could be obvious that there is another solution except this one, and that's if v is equal to 0. So if meridional velocity v is equal to 0, this holds water as well. Now, Matsuno was puzzled. I didn't put the dispersion relation here, but when you solve this for the dispersion relation and plug in n, this meridional number, -1, you get the same solution as if you imposed meridional velocity 0. So not very physical, but this is how our community keeps calling that mode. N is equal to -1 is the same as v is equal to 0 mode. OK, so what did Matsuno model from that really simple, you got to agree, simple model? He got 2 branches. Here, they look very much the same. Well, first of all, let's see. On the x-axis, we have the zonal wave number. And on the y-axis, we have the frequency. In Matsuno's notation, if frequency is positive, that means the mode is propagating westward. If it's negative, it's propagating eastward. Okay? Because we are in the adiabatic atmosphere, there are no sources. We are not going to be talking about something that whenever we do this kind of analysis, we are looking for the speed of the mode, and we are looking whether it's decaying, growing, or neutral. And because he didn't have that, all his modes are just neutral. So all we are looking at here is the phase speed of different sorts of modes. These guys up here, westward propagating, and these guys down here, eastward propagating, are called inertial gravity waves. So they can propagate westward and eastward. And the eastward branch has this peculiar mode, and that's n equal -1, which implies meridional velocity 0. That is the Kelvin wave. So the Kelvin wave is basically a specific case of a gravity wave when v is 0. OK, so that's like one group in my mind, inertial gravity waves and Kelvin waves. The other one, equatorial Rossby waves and mixed Rossby gravity wave, and those are here in the solid line is the equatorial Rossby wave, and this guy here is the mixed Rossby gravity wave. And that one propagates westward. OK, so far so good, because if I didn't say something, just ask me if I didn't define something. Because I have more equations, unfortunately, or fortunately. OK, so this is the plot. If you have been having tropical waves seminars, you've probably seen it. I put it here saying, OK, so this is very nice. Matsuno did a great job. We all cite him. As a graduate student, like that was probably the first paper that I really had to go through thoroughly. But what happens in the real world? So we know what happens in the real world, or we think we know, to some degree, we know. I usually use Wheeler and Keladi's wave number frequency power spectrum plot to see on average what lives in the tropics. And so in color here, what's plotted is OLR divided by its background. So just in essence, just think about it, the pinker the color, the more intense the disturbance is. Here we have a zonal wave number that can be positive or negative, and therefore the frequency is only positive. So if the zonal wave number is negative, that implies that disturbance is propagating westward. And if it's positive, it implies the disturbance is propagating eastward. So what do we have here that we know from Matsuno? We have equatorial Rossby waves here, westward propagating, somewhere around the planetary wave number, maybe 2 or 3. We have this mixed Rossby gravity wave. We have the special case of gravity wave, the Kelvin wave. And up here are westward much faster, so westward and eastward propagating inertial gravity waves. Now, I don't know whether it's a surprise to many that the biggest disturbance here is the MJO that we'll get into in a minute. But then the second biggest one is Kelvin, and probably Rossby comes as a third. So this is what, like if somebody asked you, what disturbances do we have in the tropical atmosphere? If you said hurricanes, you would be wrong. I mean, you have hurricanes, but they live somewhere here, easterly waves, tropical depressions, or whatnot. And as you can see, they're not that on average, they don't take that much of activity. OK, so to somehow try and summarize these 2 different groups of waves, the way I think about them at least. I call them, I say that convectively coupled Rossby-like wave. So we know what it looks like when it's not convectively coupled. Matsuno did that for us, right? But if it couples with convection, as it does in the real world, how does it look? And how do we want to think about it? So the way I think about it is, I said that's a global disturbance. Obviously, it's coupled with convection. I already said that. It moves westward. But then I think about the restoring force. And maybe that will come back, and you'll see why I think about that, like, going back to physics 101 or waves and whatever, where we learned that. What is the restoring force of the Rossby-like waves? So we have simple equatorial Rossby wave. The restoring force is the Coriolis force. That's what it responds to. If we have the special case of mixed Rossby gravity wave, then the restoring force would be Coriolis and buoyancy. Works for Matsuno, works for us. If we look at the inertial gravity-like waves, again, they're going to be coupled with convection. We saw that they can move eastward and westward. Restoring force, if it's pure gravity wave, it's just buoyancy. If it's inertial gravity wave, it's Coriolis and buoyancy. And then the special case, n is equal to -1, or meridional velocity v is equal to 0, can only move eastward. It's called Kelvin wave, but it is a real, just a special case of the gravity. So you can do the model on 3D, put v is equal to 0, and you will get the Kelvin wave. All right, so briefly, just going back to this plot, inertial gravity, Kelvin, like one branch, and Rossby and mixed Rossby as another. This we can talk about forever, tropical depressions and hurricanes. But let's think about Madden-Julian oscillation. So most people, when maybe they started thinking about Madden-Julian oscillation, they wouldn't agree that it's a wave. I think about it as a wave. I think about it as convectively coupled wave. And so I would say that it should obey some physics the same way as Rossby and Kelvin waves do. But we don't have an analog in Matsuno's model with the MJO. So before we go into the second part of my talk and I show you what I've done about this, for the past 20 years, I'm going to show you a short movie. And the voice will come.
Or as we like to call him, Mojo. He can have a big influence on Australia's weather and climate, especially during the warmest months of the year. Mojo runs eastward, moving a pulse of cloud and rainfall close to the equator, and travels around the Earth every 30 to 60 days. Mojo sends a wave of weather across the Indian Ocean, which can create cyclones and bring widespread rain events through parts of Australia. Scientists track these rain-making waves, providing updates on the intensity and timing of the next wave. Mojo mainly affects northern Australia, but can influence rain events further south, especially if one of Mojo's moisture waves feeds into a timely weather event down south. Mojo's behaviour is often unpredictable, with periods of moderate to strong activity followed by periods of little or no activity. But this dog is well worth keeping an eye on.
So I came upon this movie a couple of years ago when I was getting ready for a seminar on the MJO, and I just really love it. Great job from Australian outreach people. Okay, so maybe you don't believe me. Maybe you've probably heard lots of talks on MJO here over the years, but I believe that the MJO main characteristics, and I believe that those are very important, so when we model them, we have to get all of them right. Okay, number 2, coupled with convection, I don't think anybody doubts that. But it's a global disturbance. If we look at the Wheeler and Kiladis plot, it really lives at the planetary wave number 1. That means that its wavelength is the whole circumference of the Earth. That means we can't have 2 MJOs at the same time. And in fact, we don't. it's a huge disturbance. And if we go back to Madden and Julian discovery, okay, yes, you might not see it in OLR around the globe, but you see it in upper zonal wind. So in my mind, it is a wave, lives at the planetary wave number, L is equal to 1. And therefore, when we model it, we have to get the highest instability at that wave number. If we get the mode that has the highest instability at the, let's say, wave number 10, and much smaller at 1, that's not the MJO. Maybe that's the Kelvin mode, but that's not the MJO. MJO's wavelength is 40,000 kilometers, and Kelvin's wavelength is 7,000 kilometers. So when we compare it with the observations, when we're comparing the modeling with the observations, we really have to be mindful of those things. And yes, and it moves eastward. Everybody agrees on that. What is its restoring force, though? Is it Coriolis? Is it buoyancy? Is it something third? Oh, I hope I hope I'll give you an answer at the conclusion slide for what's the restoring force. All right, this is the second most complicated slide I have. I'm trying in this slide to say everything about my modeling in the past 20 years of the convectively coupled waves. So this is a simple analytical model. All the equations are scaled. Okay, so don't ask me about scaling. That's really complicated. Always goes in the appendix of every paper. It's messy. So they're scaled, they're linearized, and they are performed on diabatic atmosphere. And that means that we have thermodynamic equations, and that means that we have sources to those thermodynamic equations. Because these guys up here, you can write this as Matsuno's equations. Okay? So it has Boussinesq and hydrostatic approximation. These are the momentum equations, hydrostatic, mass continuity, and thermodynamic equations. This system of equations, to my knowledge, it's not possible to just impose some x and time dependence, as Matsuno did, and just note there is a different sign in front of omega here. If you impose x and t structure, you still have y and z dependence of all those variables, right? And you still have partials of y and partials of z. And as much as I try to, and as much as my husband tried to, who has PhD in math, we can't uncouple them. So to my knowledge, again, nobody has done it. The only way you can do is develop a numerical model and see what you get. So what do? Well, we opt for one or the other. So you can either have a non-rotating atmosphere and solve vertically for z. Non-rotating atmosphere means basically we're going to get rid of all these terms here. There is an f here, a Coriolis parameter, but it's scaled in here. So you're not going to have this y dependence, and you're going to be able to solve the system of equations to get a differential equation in z, and then get what all your variables look like in z. Or you impose rotating atmosphere, but then you have to be smart about the vertical structure. You have to say, okay, they all look in the vertical like this, so you can get rid of all these z dependencies. And so mostly what we do is we impose the first baroclinic vertical mode structure, just half the sign. Again, if we have non-rotating atmosphere, we can solve the model as vertically resolved. And that has worked really well for the Kelvin waves because, and maybe George Kiladis will talk more about that next week, out of all the disturbances that I've showed you, the observations have showed that the Kelvin wave is the only one that does not have this simple first baroclinic vertical structure in its fields. It actually has a very complicated structure. However, Rossby waves and the MJO, that seems like to be a good approximation. But then remember, Kelvin waves are a special gravity wave when V is 0. So if you can figure that out, and you can, and I'm not showing that part of my work, then you get the very nice observed convectively coupled Kelvin waves, for whom, and now we're coming to the most important part, where all the physics comes into convection parameterization closures. So these are the ones that I have been playing with for the past 20 years. I started with CAPE because it was back in 1999, and everybody was talking about CAPE, and all our models, some still are, have convective parameterization that uses CAPE. Then I played a lot with convective inhibition. That started somewhere in 2002 when Brian Mapes posed that as a viable mechanism. And sure enough, when I put that in, I got these beautiful Kelvin waves that exactly have the wavelength of 7,000 kilometers and look exactly like the observations. So that was pretty cool. And then in all my modeling, I usually have cloud radiation interactions, wishy, and moisture, and I will get into those a little bit deeper. All of these guys come here in these two terms. And I hope, yeah, I should be saying them for folks who are on Zoom. So all of them come here. Now, these two thermodynamic equations, I didn't tell you what do they mean or what S and S sub m are. So S, I think about it as dry entropy. You can think about it as buoyancy, or you can think about it as potential temperature. Thermodynamic equations, usually there are three of them. One is for, let's go back to meteorology 101. One would be potential temperature, one would be equivalent potential temperature, and one would be moisture. Okay, I think about them as dry entropy, which is, this is the same as buoyancy or potential temperature, or moist entropy, which is the same as equivalent potential temperature. And if I haven't confused you enough, once when you scale those three thermodynamic equations, one of them is redundant. So in other words, the scaled potential temperature plus moisture will give you the equivalent potential temperature. And so will the sources, so the source terms. OK, what else do I have on this slide? I have to define gamma. I've put this so I can remind myself. Is a gross moist stability parameter that I'm not going to go into much. We keep it positive for those who know what that is or what that does to the models. And I have this here, does weak temperature gradient approximation work? So I know some colleagues have been here, and they do a lot of work with WTG. And so I don't want to make a big deal out of it. I just want to mention it here that we have been solving this for 20 years, and WTG does not work in my set of equations. In other words, you can't just say temperature is pretty much equal everywhere. OK, so what else can I tell you about this? Well, let's move to the next slide. Model closure. OK, so here I have written those two thermodynamic equations again. So dry entropy, moist entropy, and this redundant third equation that would be, let's say, mixing ratio. So the little s plus q gives s sub m, and so do the source terms. OK, so the dry entropy is going to depend in its source terms, and I think everybody agrees on that, is going to depend on precipitation and radiative cooling. And the moist entropy source is going to be evaporation and radiative cooling. And that's pretty much acceptable. Now, what's not acceptable is how do you parameterize those guys then? And how do you do it so that you can still solve your model analytically? I'll keep it linear. The one that I'm going to spend the least time talking about is the cloud radiation interactions. The way we parameterize it is given right here. So Q is the mixing ratio. This is just the vertical integral to the top of the troposphere. And epsilon is some cloud radiation parameter. So by that parameter, it's going to increase or decrease linearly. And the simple physics behind it is if you have lots of clouds somewhere, you're going to have less less radiative cooling, as opposed to when you have a column with no clouds. Okay, so that is here in this parameter, which now brings us to moisture closure and surface moist entropy flux, or in other words, evaporation. OK, moisture mode, moisture closure, not to be mistaken with moisture mode instability. So this is like the simplest mechanism of anything that I hope is slowly replacing the way of thinking that Cape is the one who we should parameterize precipitation with. Through many talks with Pierre Bechtold, he admits that ECMWF today runs a scheme that they call it like free tropospheric Cape, but it's trying to actually mimic the moisture mode. The idea behind it is very simple, and it started around 2000 when Dave Raymond wrote a paper where he said that precipitation rate increases as the amount of moisture in the vertical column increases. And so we are here 22 years later, and you're reading this statement, and perhaps you are thinking, duh. It was not the 22 years ago. Nobody was using that. At this time, Adam Sobel wrote a theoretical paper that nobody read. Like 10 years later, he told me, I was so surprised when you cited me. I thought nobody read that paper. It was a very philosophical, moisture mode, perhaps, paper. 2000, Dave Raymond publishes this paper, and he uses disclosure for precipitation. So he says the precipitation rate is going to increase linearly with this alpha parameter, which is moisture relaxation rate, with the vertical integral of QdZ, which is basically precipitable water. You can put you can divide it by saturated precipitable water if you wish. But another piece of evidence as to why this is true came from Chris Brereton a little bit later, where he showed on the observations 20 south to 20 north, this is precipitation on the vertical column, vertical axis, and precipitable water on the x-axis. And if you close your eye, it's almost linear. But there is definite evidence for parameterizing precipitation with precipitable water. And that, and only that, is called the moisture mode. There are other definitions that came in the last 5 years, maybe, but in my mind, why complicate something that's so simple? So that's the moisture mode. That implies the precipitation rate increases as the amount of moisture in the vertical column increases. And another, now this one is maybe more tricky. People have been disputing this one. The way I parameterize the surface moist entropy flux, or in other words, evaporation, goes something like this. So E in my equations is going to go as some lambda parameter times U, the zonal wind. Goes back to Emanuel and Neela in 1987, and this is a little diagram of showing how basically what it says is that the mean easterlies are going to moisten and moisten and moisten until some kind of convection will happen. When it comes to modeling convectively coupled equatorial waves, Wishy by itself has a huge problem because the largest growth rates are not associated with long wavelengths, so it can't really model the MJO or the Rossby wave. So it was abandoned for a while until Kerry sort of doing things a little bit different. And even though lots of people kept saying, well, if you're modeling the MJO and the MJO is most prominent in the warm pool and you have westerlies in the warm pool, we have stuck our guns and we say that MJO is a planetary global disturbance and it should correspond on average to something that's happening in the tropical troposphere. And that is, or at the surface, and that is that the zonal mean in the tropics is easterly. And this is the climatology from 1979 to 2016. But what I'm trying to say here is warm pool is just a piece of puzzle. The westerly wind bursts, in my opinion, are just a result of the MJO. What really exists on average at the surface in the tropics are the easterlies. So I think that the Wishy mechanism, the way Kerry Emanuel and Neelan posed it, is pretty viable mechanism. Whew, OK. That's the first or the second most complicated slide. I promise everything after that gets easier. Before I go into this, I want to mention, though, that Okay, you've seen the equations. They become way more complicated as you go to higher meridional numbers. So that's why we really like working with v is equal to 0 or n is equal to -1 case, because it's mathematically much easier. Another thing that you always have to pay attention to is that you are trying to model the equatorial waves, which means they can't exist at the pole. So when you're solving your meridional wind v, you gotta make sure that, well, when you're solving for v or anything else, you gotta make sure that as you are moving away from the equator, that mode doesn't blow up. It has to decay as you move away from the equator. And many solutions to the analytical models don't. And that creates some confusion in what are we actually getting. So I'm going to show two sets of results. This is more complicated. So one is going to be for the MJO, one is going to be for the Rossby wave. So I have chosen to show you the results on rotating atmosphere, where we only have the first baroclinic mode structure, so I can't get the Kelvin waves, obviously. What I do get are called eastward propagating Vichy moisture mode and the westward propagating. And here we are only looking at the eastward one, which really resembles MJO a lot, so I'm calling it MJO. Top here, we are looking at the case n is equal to -1 or v is equal to 0. Some might say, well, that's just the Kelvin wave. Well, it's not. I'm showing you here a plot of growth rate of the mode as a function of planetary wave number. And remember, the MJO lives at the planetary wave number 1. So if we don't remember, so the three main mechanisms are moisture closure, cloud radiation interactions, and Vichy. And in my earlier work, I thought all of those were really necessary. So it came as a surprise in 2017 that without cloud radiation interactions, at least for v is equal to 0 case, you can get the MJO-like mode that is unstable only for long wavelengths. If you add cloud radiation interactions, it becomes unstable for all the wavelengths while still keeping the largest instability at the planetary wave number 1. And now why am I emphasizing all this? Is because there are mechanisms that don't have scale selection, there are mechanisms that do. And if you're trying to find something that truly is behind your disturbance, then you're really looking for this zeroth order most important term. What can I say about this mode? It has no analog with Matsuno modes. And when you're calculating carefully your modes, even when you go higher up in the meridional numbers, you can always go back to the most simple things, right? You can always turn off things and see what do you get. And therefore, when you do Kelvin wave, you have to be able to get the Matsuno's Kelvin wave if you set certain things to be 0. No matter what you do with this mode, you're not going to get any Matsuno mode. So it has no analog with it. It's eastward propagating due to Vichy, which I'm not showing here, but I'll show it in the bottom plot. And it's unstable only for long wavelengths. Now, the MJO in reality does have a meridional component, and although it might not be the most important one, it does have it. So the same model equations also model eastward propagating Vichy moisture mode for n is equal to 1 mode. But then it has to have cloud radiation interactions. So what we are looking here is the planetary wave number on X. Upper panel is the propagation. So eastward propagating if it's positive, and bottom panel is the growth rate. So the black line is CRI and Vichy. Propagates eastward, has the largest instability right here. If we do small Vichy, I just put that here so you can see that Vichy gives propagation, at least in my model. If I don't have cloud radiation interactions, it blows up. That's the one where it's not going to decay as you move away from the equator. So that mode exists in n is equal to -1, but does not exist in n is equal to 1 case. So in more realistic world, we would need cloud radiation interactions to make it work. So eastward propagating due to Vichy, unstable due to both Vichy and CRI. And a schematic trying to show you the conceptual picture behind it is this. So we have moistening via wishy. So this is that easterly. It's moistening, and it's moistening. It can take days or weeks. So it's not just wishy, it's just moistening, and then right above it, we're going to have deep convection. No, it's going to moisten and moisten and moisten until it reaches some critical value, at which point we're going to have the maximum moisture in the column, and there comes the moisture mode closure right here. And because that moistening is happening on the east side, it's moving east, and this westerly here is just a consequence of the deep convection. Not that the convergence is creating the convection, but that the convection is creating this westerly, at least in my model. So this is the schematics of my model. And the Rossby wave looks a little bit different. Remember, it has an analog in Matsuno's world. So we are looking here, again, planetary wave number, phase speed. It's better be negative because it's going to move westward. I have plotted, because we do have an equivalent now with Matsuno. In black is if it was just the Matsuno mode, right? So propagates westward, like right here, and it's neutral because it has no source terms. Now in red is how does that mode look like with cloud radiation interactions and wishy, and the blue one is with no cloud radiation interactions. And it's basically saying that the phase speed is pretty much the same, and that it's going to be unstable for long wavelengths due to wishy, and then become stable unless we include cloud radiation interactions. So a little bit similar to MJO, well, not really. This is n is equal to 1 mode, and it does not blow up without the CRI, but we know that the Rossby wave should be living somewhere here, like 2, 3 maybe. So I would say that it does need cloud radiation interactions, which exist in the real world. OK, so we have an analog with Matsuno mode. We know it's restoring forces Coriolis. It propagates westward, not due to wishy, but due to beta effect, the same way as Matsuno's mode does. And OK, that we already addressed a little bit of diagram, because I still have a third part of the talk and not that much time. Rossby waves diagram will look pretty different than MJO. The one that I showed you on MJO did not have a meridional component. Keep that in mind. I showed you the n is equal to -1 case. Well, this is n is equal to 1 case. We have x and y, right? In my model, what happens, because I'm imposing wishy, it turns out that in the area of the deepest convection, I have divergence of zonal wind. But that divergence is so overly compensated by meridional convergence that it's converging right there, and that's where the deep convection is, and I call it the wishy moisture mode, propagates westward due to the beta effect. All right. Whew. Any questions? I mean, this is more of the same, but I thought I was done, truly, with the moisture modes, MJOs, Kelvin waves, Rossby waves. I don't know how many of you in this room remember Andy Maida, who was trying to figure all this out. And when I was a graduate student and tried to pose the idea that the MJO has something to do with the moisture mode, he stood up and he trashed my talk. He told me I should read more papers. There were about 400. I don't think I have ever been at a conference that big. There were about 400 people in the audience. It was 2006. 2007, we were together at the same workshop, and he had this mysterious X parametrization that he wouldn't tell anybody what that was. Later on in the papers, we saw that it was the moisture mode. He had excellent postdocs and students. So anytime you have conflicting theories with somebody, those are people you want to talk to. So that helped me kind of understand. Well, I can't claim still that I understand Andy Maida's models. But anyways, what I want to say is I thought I was done, had this beautiful advice from my advisor, Dave Raymond, that your whole life and your whole research should not be based on what you've done for your PhD. So I went and did other things. But then Then I kind of got ticked off by having more and more theories about the MJO. And I thought, like, instead of trying to understand the theories we have, which, trust me, are really hard to understand each other's theories because of the non-dimensionalization, because of scaling, because of a million other things, it's really hard to understand somebody else's work. So I said, well, why don't we try to go from lots of theories to less theories? And the recent review papers on the MJO say that there are, I think, 7 theories. And so I said, well, Carrie, Emmanuel, I've been looking at your model since I've been a graduate student. See what you've done in the last couple of years. What if we can bring our 2 theories together? So that's what we try to do. Fuchs and Raymond model, so rotating atmosphere. We used Vichy, moisture closure, and cloud radiation interactions. Khorudinov and the manual model had Vichy precipitation efficiency, cloud radiation interactions, damping effect of boundary layer entropy perturbations, and diffusion. So he had a whole bunch of stuff. After he just did Vichy and didn't get the right result, he decided he needs much more. So he put much more. He did the analytical model and the numerical model, got beautiful MJO, beautiful Rossby wave, beautiful even mixed Rossby gravity wave. But he has all this stuff, and it's hard to understand what's going on. So we said, OK, let's get rid of a whole bunch of parameters. And I don't have that slide because I thought it's too complicated. But if there is a question, I have it to show it. So essentially, we got rid of these damping effects and diffusion. And we said, OK, this precipitation efficiency is similar to moisture closure. He uses the mass flux approach. We use the moisture budget equation. But essentially, you know, if you play with it long enough, and we both played with it a lot, you get 2 thermodynamic equations. So this is a minimal difference model. This is bringing those 2 models together. Fuchs and Raymond, the ones you've just seen, epsilon is the cloud radiation parameter, lambda is the Vichy parameter, and alpha, we just said it's 1, like the non-dimensional alpha. So we lost that parameter. Basically, it's moisture relaxation rate, but in its essence, it says that it takes about a day for the moisture mode to work, as opposed to like Betz-Miller closure that has 2 hours. And it's pretty accepted by now that it's about a day. OK, and then Khorudinov and Emmanuel model has this additional term. So this is, again, all scaled, non-dimensionalized in the same way, so we can actually compare. It was a nightmare of a year. But there's only this additional term. That's the only difference between the 2 models that had such a different starting points. And the results, and I can show you for higher meridional numbers if you would like to ask that question. This is V is equal to 0 case, the simplest one, right? So we are trying to model from the minimal difference model the eastward propagating mode that's propagating eastward and that has the highest growth rate at the planetary wave number 1. And in red is Fuchs-Raymond model, and in blue is Khorudinov-Emmanuel model. And when we saw that, we were like, wow, this, I mean, whichever one you want to take says exactly what the MJO is. It's moving eastward, has the greatest instability at the largest wavelengths. If you plot its structure and whatnot, it looks like it should look in the observations. And there we go. You know, there is like 2 theories that are said to be different, basically saying the same thing. And yeah, it has taken 20 years, but here we are. In conclusions, I don't want to write a whole bunch of conclusions. But in conclusion, I want to say, OK, so what do you think is the restoring force behind the Madden-Julian oscillation? Do you agree with me that MJO is the equatorial wave? So OK, so it's not Coriolis, it's not buoyancy. I mean, I've struggled with that because I started like, OK, come on, I've got to know some basics here, right? And neither MJO nor the Rossby convectively coupled Rossby wave, but especially the MJO, would not exist without the moisture mode. So in my opinion, that moisture thing can be considered as a restoring force. One could argue that cloud radiation interactions could be too. It's just that, well, no, both don't have scale selection. They can exist anywhere. But okay, it's definitely something that has something to do with non-adiabatic atmosphere. Can it be a force? Can it be a restoring force? I don't know. One new way to think about it. Thank you very much.
All right, we got time for questions and comments.
Thank you. So going back to the moisture mode as a restoring force for MJO, do you refer to boundary restoration, or like just could you elaborate on like what you mean by moisture mode itself as a, because like it's, you know, Coriolis or it's force that you can.
I agree with you that you as Coriolis force or buoyancy go, you can't really call that a force. But if you like what, okay, let me back up. When I first started playing with the model, I had cape closure instead of the moisture closure. So instead of saying precipitation is equal to some parameter times the precipitable water, I said it's equal to some parameter times cape. I did not get the MGL. And then I did that. I did the moisture mode closure, and I got this new eastward propagating mode that was not the Kelvin mode. So I would go back, like in my mind, I would go back to that and say, like, what MGO cannot live without? And it's not a boundary layer thing, because it's precipitable water, right? It's the integral over our column in troposphere. How it can be classified as a force, I don't know. So maybe the terminology here should be defined better. You had a question? Rich, here.
Where's the question?
Thanks. Really nice talk and very clear, given we have so many MGO theories.
Thank you.
So if you have a mode that's unstable in a system, then in the observation, there should be something that stabilizes it. Like in the mid-latitude, we have baroclinic eddies, and you have nonlinear eddies, which dominates the momentum budget, and that's how we understand it stabilizes a growing mode. But if you have an unstable mode in the tropics, then what is stabilizing it? Like if we look at the momentum budget for an MJO, it's all the linear terms that they're in the intraseasonal time scale.
Yeah, no, that's an excellent question. And you're not going to see it here, right? Because the analysis here imposes a function. It imposes that all your variables depend on in time as the exponential of minus I omega t. So you can either get the growing, neutral, or decaying mode, and you don't get the time evolution of them and what happens that afterwards and when and how they die. You just can see which mechanisms make it growing or not growing. So if they are growing in time, then they're unstable. If they're decaying in time, then they're stable. And you don't care about them because they go away. If they grow in time, you care about them. But obviously, that does not. We've tried and played with it a little bit to try and get some time continuous and some other mechanisms, and then see what happens afterwards. It's very hard to do it linearly.
Sure, but do you have a physical intuition, like what processes could be?
So why would MGL all of a sudden disappear, in other words? Would that be the question?
Or doesn't blow up doesn't blow up into a hurricane, for example. Or
Well, some hurricanes, yeah, we sometimes have some nice hurricanes because the MGO is active. So obviously it influences all the other weather. honestly, as it propagates around the globe, it's gonna at some point dissipate. Obviously, when you look at the worm pool, that's where the most of the precipitation is. What changes and how it gets killed? I mean, but you don't think about it as blowing up. Like it's just growing in time. That just means the disturbance is there. It doesn't mean it's blowing up.
Thank you for a great talk. In terms of, I had a couple of questions about your moisture mode. One about the closure. Do you need, like, there's the work by David Nealon, Ole Peters, and I think later on with Sam Steckman also about the non-linearity in terms of triggering convection, and the maximum variability is at a certain trigger of a certain threshold of total column water vapor. Do you need to include that in this model to?
No, I do not.
Okay. And then a second question, which is more related to the moisture mode instabilities. Do you need spatial gradients in moisture to support?
Okay, so there are two things. One thing is moisture mode, and the other one is the moisture mode instability.
Yeah, exactly.
I try not to talk about moisture mode
Right.
instability because it gets confusing.
Yep.
So the moisture mode is this.
Yeah.
And the moisture mode instability is usually because of the negative gross moisture stability, right?
Yeah.
And then effective moisture mode instability is, we like to add cloud radiation interactions to that because they act in a similar way. I have really worked hard with the gross moisture stability thing because the gross moisture stability is not negative overall. And so saying that the MJO is it has the moisture mode instability, I think would be wrong because then we would have it at all scales. So all my work is with positive gross moisture stability, or at least let's say all my late work is with positive gross moisture stability because of that. Now, moisture mode instability, I more think about as similar to self-aggregation.
Okay, so convective self-aggregation.
And it, yeah.
Thank you.
There was a question here.
Thank you very much. Hi, very nice talk. I have a question. Could you go back to the Kilatis frequency plot? This might be a little bit different from MJO, but I'm wondering, because on the weather map, we see the roll-up of ITCZ due to Kelvin-Helmholtz shear instability, and that will cause tropical cyclone genesis over the Eastern Pacific. So I'm wondering, where is the place of such shear instability in this plot?
Yeah, well, it's a good question. It's a question that I sometimes was like, where is that? The best answer I get is it's right here,
Okay.
where we put the easterly waves. But right, the Eastern Pacific, it doesn't have to be the easterly waves, at least not the African easterly waves. When it comes to how much on the average it produces OLR or whatnot, I think this is pretty correct. The MJL really is the disturbance that brings the most rain on the planet on average, way more than all hurricanes combined. When it comes where it is in the wave number frequency plot, is a good question. And I think Rosie and Rich are trying to work that out, because you could think about the easterly waves that are here.
Yeah.
If you could only have a Rossby wave that didn't do a stupid thing like this, it just went like that. Wouldn't that tell you something about it? Easterly waves, to my knowledge, are extremely difficult to model analytically. I've tried once or twice, and I was so frustrated that I gave up. I think you have to really like numerical modeling to attack those and try to maybe find some new physics in it.
I see. Thank you very much.
So staying on that topic a little bit, So we all know this figure and kind of take it for granted. But the more I look at it, the more I think I don't see what I'm supposed to see. If you take away all the lines, all the black lines, the dispersion relations in all the boxes, and just have the colors, it looks like a V, right? So almost symmetric, not really symmetric. And then you're adding the dispersion curves over it, and I always feel like, okay, the power should follow the dispersion curves if those features are really there. But I don't think they do. So what you just mentioned, the equatorial Rossby waves, well, there is some area there where there is overlap, but it looks like it's just almost like Kelvin waves going westward. And then, we say mixed Rossby gravity waves are there, but they're not really there. It's just this whole spectrum, broad spectrum. And so I'm saying, I don't know if we're actually seeing what we think we're seeing.
Yeah, I would agree with you, especially here for inertial gravity waves, because I don't really see anything there, right? Yeah. Okay, so this is symmetric component. There's the anti-symmetric one where you have the OLR. So that my first answer is if you look at the symmetric and anti-symmetric plots, you'll see more. Because somewhere here there are boxes for disturbances that are not symmetric. But when it comes to MJO and ER, they should be seen here, and the Kelvin should be seen here. And yeah, maybe we are ballparking, and I don't like these lines at all because the way that they have derived them. Remember when I started with Matsuno and that capital H? Well, it's sometimes called equivalent depth, and what people have done in the beginning, instead of trying to parameterize the precipitation terms and whatnot, they fiddled with that capital H to slow down the disturbances, because we knew from the observations that we don't get such a fast equatorial Rossby wave or such a fast Kelvin wave. Kelvin wave is 48 meters per second. In reality, it's about 15, 17 meters per second. So they just filled with the equivalent depth mathematically to get these lines that you see here. So that's I forget what's the H here, the equivalent depth. My answer to it is, yes, you actually make a good point, because maybe that's not the best plot to look at it, is if you add convection, if you add convective processes to it, and then remove them one by one, you get what you get, and then at the end, you get the Matsuno's mode. And so if you can have an equivalent when you're coupling it with convection to the one without, then you can group it in that. The rest is really observations. The fact that the Kelvin wave has a wavelength of 7,000 kilometers, that's observations. And there have been way more than what is shown on this plot, right? And that's how we know how the MJO looks like in the vertical, and et cetera. But yeah, you're right. I mean, and also it says here that the MJO can exist at wave number 2, and we've never had 2 at the same time. If you talk to Kerry Emanuel, he's going to be like, come on, you can't do anything continuous. Zonal numbers can be only 1, 2. There's nothing in between. So there's a lot of things here that could be up for, questioning.
On that similar note, do we know why, like, the inertial gravity waves do not appear in any of these theories?
Wait a second. Yeah, no. I don't think even Kerry has that. He has mixed Rossby. Okay, so I'll tell you my opinion. I think the gravity waves respond to the same physics as the Kelvin wave. I think Kelvin wave is like really the simplest way of studying gravity waves. Inertial gravity waves are therefore, they're like inertial, so they should have Coriolis. They should be on rotating atmosphere, and in my opinion, they should be vertically resolved, or we're not going to capture the mechanism that makes them unstable. And I have never been able to solve for Y and Z at the same time. So I have never been able to get inertial gravity waves, and I have never been able to get the mixed Rossby gravity wave due to that reason. But in numerical simulations, they show up.
Okay, we'll take one last question.
I had a question about a different coupling, which is ocean-atmosphere coupling. like none of the theories talk about ocean-atmosphere coupling, and there's recent work by Adam Rydbeck and colleagues at NRL looking at MSC budget plus upper ocean heat budget, showing that upper ocean heat contributes to the building of MSC in a MJO unstable mode. So is there a way to extend this work, coupling it to a simple upper ocean?
Well, if you know somebody who knows how to add something analytically, linearly into this, I would be happy to look into it. We have done some, okay, it's not really what you're saying, but we have added this model, Fuchs-Raymond model, to a simple Gill warm pool model, for instance, and so that then the MJO slows down. So that's, for instance, how we explain that. I'm sure that there are ways to add some coupling, but still analytical. As long as, if you find somebody, let them do the work. I'll just, because I should move away from this.
Thank you.
All right, thank you very much.
Thank you.